All right, good evening. Sorry for the slight delay here. To chair the school curriculum meeting. So we have one applications left to teach on double integral. So let's finish that. And this is the topic on moment of inertia, right? Because this is double integral, more precisely, it's about moment inertia of the area. Okay, so this is not the moment inertia of a 3D object yet. So when we learn triple integral, so we'll be able to get a generic moment inertia about a 3D object. So here is double integral. So we're talking about moment inertia of a, so you could call it 13 thin plate represented by the region R. But essentially, it's the moment inertia of the area. Now, alternative name is called, actually it's called the second moment of the area. Second moment area. So actually, as a matter of fact, if you recall that, you might wonder, so what is the first moment in area? We learned that in the previous lecture. So first moment, okay, of area, and that is defined by triple integral. For example, this is a moment about the x-axis, so this is density. Okay. Right, so this is an example formula for first moment area. So this is area. If you recall, this is area, and this portion here is like a dm. So mass times the distance to the y-axis, which is x, and you got a mass moment. So it results in the first moment of area. And similarly, you can get a first moment of area with respect to the x-axis. So both of these, right, are first moment area. So let's look at the second moment area or moment inertia of a certain area. Okay, so let's do the easy one here, just to jog your mind on some of the very basic physics concept. Okay. So first of all, what is the definition of mass? Okay. So when you talk about the mass, okay, what you're really referring to is how hard is it, okay, to impart a translational motion. So you've got a mass, you know, you say, okay, this guy got a big mass, that guy got a huge, smaller mass, right? So what does that mean? It actually means basically how hard is it to impart a translational motion, right? And then the concept of a moment of inertia. So let's call this is MOI, right? That's shortened as MOI for moment inertia. And first of all, moment inertia, whenever you talk moment inertia, it's always about an axis. So moment inertia is a quantity about a certain axis. The axis could be anywhere, you know, you can define the axis either way, horizontally, vertically, or inclined, right? It's a rotational axis that you're gonna rotate about. So if I use the same type of language here, then I would say moment inertia basically means is how hard it is, okay, to impart, okay. So I want you to finish the sentence. What do you think? What would be the next keywords? Mass is how hard is it to impart a translational motion? So moment inertia should be how hard it is to impart. Exactly, rotational. Okay. So that's the nature of a moment inertia. So let's look at a couple formulas, derivations of a couple formulas here of how this moment inertia is derived. So first, Okay, since moment inertia is about an axis, so we actually will look at the formulas about this different kind of axes. Okay. So first, let's look at the moment inertia about z-axis. Okay, so this is the drawing like this. Okay. So suppose you have a region R or very thin plate, and then you're interested in what is the moment inertia of this region R, which is in the area about the z-axis. Okay. So you're trying to rotate this region R around this z-axis, and then you're interested basically to find the moment inertia. And when this is about z-axis, okay, we have a specific name, and this kind of moment inertia is called a polar moment of inertia. So again, more or less, the polar moment inertia of this area. Okay. When we deal with 3D objects, then we don't need to keep the area anymore, right? So it'll be polar moment inertia of the 3D object about certain axis, okay, a z-axis. Yeah. Okay, so let's derive this formula at here. Okay, let's start from the simple case. So let's start with a point mass. And I'm going to draw a little illustration at here. So let's say I have a point mass right here, okay, denoted as M. Okay. And this point mass is undergoing a certain type of motion, okay, along a curve, for example. Okay. And then you can sketch, okay, a velocity, right? And its position, okay, it will be R at here. Okay. And after a little bit of time, okay, and let's see, right? The point mass experience an angle of rotation theta. And point mass move from here to here, right? Okay, so technically it moved a displacement given by this arc length, right? Yeah. So let's derive some very simple formula together. First, we're talking about speed. Speed is V. Speed is equal to the displacement over the time, so delta S over delta T. And delta S, as I said, illustrated here, I mean, you're moving from this location to this location along that arc. So delta S will be the arc length, right, for this little distance. And arc length, right, if this is a very small angle, then arc length is equal to R times delta theta and divided by delta T. Okay, so that's your speed. So basically your speed, right, is equal to R, right? You change the delta to differential. So basically you consider it's a differential concept, then you got d theta over dt, okay, times R, and that's your speed. And d theta over dt technically is called the angular speed. So it's called R omega, right? That's how fast it's rotating around this z-axis. Okay. So that's your speed. Okay. So now let's look at the kinetic energy. The kinetic energy formula is 1/2 mv squared. 1/2 times mass times velocity squared. Okay, so I got my velocity right here. I got my velocity, which is R omega. Okay, and then I'll just calculate it. So mr squared omega squared. Okay, so now I got instead of 1/2 m squared, I got a different expression for the kinetic energy, which is in terms of omega and the R at here. Right? So now I'm going to define a new term. So this term at here. Okay. So I'm going to let or define, let's call it I naught equal to mr squared. So we define this mr squared as a new symbol, call it I naught. Then your kinetic energy will basically equal to 1/2 I naught omega squared. Okay, so now you can clearly see a little bit comparison here, right? You see your kinetic energy could be expressed as 1/2 mass times speed. And then here is 1/2 some quantity times angular speed. Right, so this V, which is linear, and this omega is angular rotational, and this m is mass. So the I naught, right, must be a quantity associated in analogy to this mass at here. So this I naught, okay, is basically called the moment of inertia, okay, of the point mass, okay, with respect to the z-axis. So that is a formal definition of the moment inertia of a point mass with respect to the z-axis or certain axis. Okay. So the reason is with respect to z-axis because you see the distance here, r, that's the distance from the point mass location to the z-axis location. Okay, so you do need to be rigorous in terms of this definition, right? So the r at here, as I said, is not an arbitrary r. It has to be the distance from the point mass, okay, to z-axis. If this distance is from the point mass to some other axis, then you got a different actually moment inertia, right? Yeah. Okay, so now we will expand from here, right? So your I naught, okay, is formula mr squared. We're clear now. This is the formula for calculating moment inertia of a point mass with respect to z-axis. Okay, so then I'm going to expand from here to not just the point mass. Let's look at the moment inertia of the thin plate. And by that we mean basically, and then thin plate, let's see. Okay, I'm going to call this is about z-axis. Okay, yeah. Okay, so let's draw this diagram here. So this is your x, this is your y, and this is the thin plate represented by region R. Okay. Right. So let's start from simple. Let's start from one single location. So let's pick a location. Let's see, this is a location xk, yk. Okay, the location within the region R. And then I take a very, very small patch, okay, around this region, around this location, xk, yk. And so you have a very small patch at here. And you can call this delta A, little area. Okay. And because it's a small area, so you definitely can have a very small mass associated with that small area. Let's call this delta mk. Okay. So that's a mass associated with that little patch. Now consider this is small, okay? It's a very, very small patch. Then I could assume this is a point mass. Okay? If I can assume you have a point mass at here. If this is a point mass, then the question is, what will be the what will be the moment inertia of this point mass with respect to the z-axis? Okay, so then I can use my formula here, right? I can get the point mass on moment inertia by the z-axis is the mass of the point multiplied by the distance from the point to the origin, right? And the distance from here, let's call this RK, right? This RK here, okay? So apparently, what is RK? RK is RK square, yeah. RK square is x squared plus YK squared, right? And that's the location of the point mass. Okay, so this is basically, let's call this IK, right? So this is the moment inertia of the point mass, K point mass in respect to the z-axis. But we're not looking just for one location, right? We're looking for the whole region at here. So then guess what? And then you're gonna add up, right? All of this, right? All of this moment inertia, right? And then we can let this angle to infinite, right? As 0, that's what we always done. Then this summation sign become double integral. Okay. And what are we integrating? So we have this, we have the R square here, right? So R square was be x squared plus y squared. And you have delta mk, so which will become dm. So dm basically is your density times the little area, right? So this is your dm. Okay. So delta is the density. Okay. So delta xk and delta xy is the density function. So now you get a double integral, and this double integral at here is basically the moment inertia we're looking for. So we call this is I naught, and that's the moment inertia of this thin plate with respect to the z-axis. Okay. And you can clearly tell this next time if I present you with this formula, you might wonder, so what is this moment inertia, right? Because moment inertia always is about an axis. And you might wonder, so which axis is this with respect to? So how do you tell? You should tell that by looking at this term. Okay. Looking at this term, so what kind of distance does this term represent? And clearly this represents the distance from any point to the origin or to the z-axis. Okay. So there you go. So this is a formula for calculating this moment inertia of thin plate about z-axis. Okay. Yeah. So then the natural question you should probably can think of is, okay, so then how about the moment inertia about some other axis, right? Or some other arbitrary axis. So we can certainly look at a special axis. So how about moment inertia with respect to the x-axis? Okay, yeah. So with respect to x-axis basically means, so this mass or this thin plate at here, okay, instead of rotating around the z-axis, so now you're trying to rotate around this x-axis, right? And trying to get the moment inertia, right? So use the same idea, okay? Here needs to be the distance to that rotational axis. So if I'm looking for the moment inertia about x-axis, I'm not going to change anything to the dm. So the only thing I'm changing here, this quantity here will be the distance square. Right? So this is distance square, and distance is from anywhere on the thin plate to the x-axis. So this portion here must be this y, right? So here you need to insert a y square at here. So that'll give you the moment inertia with respect to the x-axis. So similarly, and you can write down the moment inertia about the y-axis. So that'll give you the moment inertia by the y-axis, right? So this is the distance from the distance squared from any point on thin plate to the y-axis, which is the x coordinates. So overall, these are the formulas, okay, related to moment inertia that we will use, okay, for any possible exam questions. Okay. So let's take a look at an example. Okay, let's see if I got a thin plate represented by x squared plus y squared equal to a squared. And the density is 1. Okay. It's a very simple region. That's basically a circle centered around the origin with radius of a. And density is 1. Okay. So let's calculate what would be this I naught. Okay. So I naught essentially represents the moment inertia about the z-axis. All right, so I'm going to use my formula. So if I pick any point on the region, on the in the region, right, and then from the region to z-axis or the origin, you got a distance r, right? That's where this r from. Right? I mean, if you want, you can certainly write it as x squared plus y squared dA, and that's okay. Yeah. But this backs for the question basically. Okay, when you get a double integral, okay, and your next thinking should be, okay, should I integrate using Cartesian coordinates or should I integrate it using polar coordinates? Okay, yeah. And how do we decide that? Then you look at the region. Okay, if the region more or less has a circular type of functions involved, then chances are you should use polar coordinates. Okay, yeah, most of probably. So we should consider polar. So let's use a polar coordinate to calculate this thing here. If I use a polar, that's where this x squared plus y squared turn into r squared. R squared and dA is r dr d theta, okay, for polar coordinates. Then the next step is to find limits for r and theta. And that should be pretty simple for this question, for the region here. So what you do is you draw an arrow line out of the reading line out of this region at here. And first contact give you r mean, second contact give you r max. And then you rotate this reading line starting from z x-axis, right, all the way back here. And obviously it's 0 to 2 pi, okay, as the two boundaries or edges. So then you can calculate this, and that's a very simple calculation double integral. So you get pi a to the power 4 divided by 2. So this is the moment inertia of this thin plate with respect to the z-axis or the origin. Okay. Any question regarding this example here? So now let's make it a little bit more, just a little bit more difficult. Okay, so suppose that this is the same thin plate, okay, with the radius of a. Okay. So now I'm interested to find out the moment inertia of this thin plate with respect to this axis, okay, E prime axis, for example. And that axis, okay, pass through a point on the edge of the thin plate or the circle. Okay. So it's like if you play a game, you know, how you rotate this thin plate, right, around the an axis passing through the edge of this area. Okay. So we need calculate, let's call this IE, okay, equal to what? Okay. All right. So first thing to do is, okay, you need to establish certain formulation to describe this situation properly. So what we could do is, right, we can establish a coordinate system. Okay, here's the XY coordinate system. I'm going to place the circle or the thin plate, okay, like this. Okay, and your z-axis or your E prime axis is right here. It really doesn't matter where it is. You can always establish your X, Y, Z like that, right? So basically you're considering E prime as the Z axis, and then you establish your X, Y accordingly like this. Okay, so now once you get this laid out, then this IE, right, is basically translated to a problem in with respect to this graph. Then what is the moment inertia about the origin or z-axis? Then you calculate this IO now, right? So that's equivalent to calculate the IE over there. Okay. So how do I calculate? Same formula. So you calculating since this is about the origin, so then you need to use this formula, right? X squared plus Y squared dA. Again, this is a circle, right? I think I'm going to use polar coordinates. Okay. So polar coordinate will turn x squared plus y squared into r squared, and this r, and then dr d theta, right? Okay. Okay. I guess the tricky part is, and let's put down this empty here. Well, how do I find the limits now, right, for the r and the theta? So let's take a look together, right? Okay. So first of all, okay, this is a circle. What would be the circle equation here? So if I write down the circle, sketch a circle like this, can you write down the circle equation using Cartesian coordinates? Right, that would be a very basic skill that I expect that you that be able to write it down. Right, so the circle has a center at A0, it has a radius of A. So the circle equation is x minus a squared and plus y squared equal to a squared. Okay. All right. As usual, so let's follow the process of finding limits. Okay. First step, you draw a reading line, okay, out of the region R. First contact give you R mean. Okay, so R mean is 0. And second contact give you R max. So R max, unfortunately, not going to be constant. If you draw it here, right, it's a different length for R max. Okay, so we need to find an expression for R max in terms of a theta. Okay, so that's the tricky part here, right? Okay. So here's one way you can do it, right? You can make use some high school geometry. So you can create a triangle like this. So basically connect the R max location to the other side of the circle. Okay. Then this is going to be a right triangle. And within a circle, if you use the diameter as one side and then use any point on the circle, create a triangle, there will be a right triangle. Okay. So you got a right triangle right here. And the hypotenuse of the triangle is 2a. And you're looking for this side, which is R max. The angle here is a theta. All right, so can anybody tell me what will be the R max? Expressed R max using 2a and theta. And that should give you a 2a times cosine theta. Okay. So this is where you put it on 2a times cosine theta. Okay, so next step, you rotate this reading line, okay, from one edge to the other edge to find the angle associated with the two edges. So apparently one edge is over here, the other one is over there on the top. So theta goes from, right, so this is this angle. For this angle here, guess what? You can use negative pi over 2 because, right, it's on the negative side. And then the top there, and that should be pi over 2. Good? Yeah. So now you have the layout of this double integral, and you can calculate the rest of the calculation, okay, as they are. Okay. So I think if you do the calculation, now this calculation turned out to be a little bit cumbersome actually. So take a look at the lecture notes. It does require you to use a formula for cosine to the power 4. But you're gonna get 3 over 2 pi a to the power 4. Yeah. Okay. So take a look at this one here, because this is not as simple as you think. So it does require a little bit of technique, integration technique. Okay. So that's the idea, right? You can see how you can calculate the moment inertia about an arbitrary axis, but you have to set it properly here. Okay. So let me ask a question before I move on in here. Okay, so this is just a quick thought regarding the circle. Okay, assuming that you have a region R, which is this. So let's say you have a region R like this, and you're required to integrate certain function over this region R. So how would you approach this? Do you want to use Cartesian coordinates or do you want to use polar coordinates? Polar, okay. So let me see who wants to use polar. Okay, good. So I'm going to use polar, right? Let's see if you see any problem here. So if I use a polar, then I need to find, okay, whatever the function here, I need to find the limits for the R, right? So if I use my generic approach finding R, I'm going to draw a reading line, okay, out of this origin and cross this region R. Okay, and then first contact, R min. Second contact, R max. So somebody tell me what's R min, R max? Can you? Now be careful, raise your hand. Because you can't, right? Yeah. So bottom line is the polar actually doesn't work. Okay. If you try Cartesian, okay, chances are it might work, but it will be very cumbersome to calculate out this whole integrals. Okay. Yeah. So here's my question to you. So what would work? What approach works? We learned. Yes. Sorry, come again. A Cartesian, I said it might work, but it will work very ugly in most cases. So you want to, yes. Substitution, but that's not the name we use. What's the name we use? What's the technique? The name of the technique we used. Change a variable. Okay. So how would you change the variable here? Give me an option. How would you change the variable? You have x, y, so you want to change to what? You want to change the u and v. So how would you change that? Exactly. Okay, you use this change variable. Why? Because if you use this change variable, how does the region R become? The region R becomes, it becomes this circle. It's the same radius, but the circle moved from a different center to the origin, right? And that we have done that quite a lot. You know, we never use the polar coordinates on the circle center around the origin, and it always works, okay? And it always works, sometimes, most of the time, work easily. So this is my point here, right? So change a variable. Again, the reminder is, if you have a question and you try it and you end up with an ugly computation or not doable kind of situation, right? So you need to think what I'm saying next. That's not going to be my intention, right? My intention is never to give you another situation like that. So you need to think otherwise. So what should we do, huh? Yeah, to make it simpler. So there got to be a way to make it simpler, okay? Yeah. All right, so that is pretty much everything about this applications of double integral, okay? Yeah. Okay. But I think I wanted to touch upon one more theorem. I think it is kind of important, which you have learned. Okay. Let's think about this parallel axis theorem. I think you learned this. Did you learn this in your dynamics course already? Okay. So what parallel axis theorem says this, right? Suppose you have a thin region R at here, okay, and it has a center of mass at this location, for example. Okay. So this location is CM, or center of mass. And then you can certainly pass an axis through this center of mass. So a lot of time you probably, if you look up engineering handbooks, okay, a lot of time you get a quantity called moment inertia about the center of mass. Okay, so that's a quantity, especially for regular geometry, and you can find a quantity easily from engineering handbook. Okay, so that's IM. It's a moment inertia of this thin plate about that axis going through center mass. Okay, so now a different situation is you create a different axis. Let's call this a U axis. Okay. And this axis is a distance of d, okay, from the center of mass axis. And we want to calculate the moment inertia about this new axis, okay, the U axis. So parallel axis theorem says the center mass, this moment inertia about this U axis equal to the moment inertia around the axis going through the center mass, and plus the area of this region or the thin plate times d squared. Okay, so that makes your life much easier. You don't need to calculate double integral again around this IU. So you could just use this formula to get the IU. Okay, so let's try this parallel theorem to the examples that we have done. Remember this example, right? You know, first we calculated, where did you go? First we calculate a moment inertia of the thin plate around this z-axis, and this is a density 1. So basically, for this thin plate, the thinner mass is right on the origin, right? And then we calculate the moment inertia about an axis passing through this origin right here. So we did use double integral to do all of these things here, right? But I can use parallel theorem to calculate. Essentially, you have an axis. This is your U axis, right? and then this is your distance. And in this case, the distance is the radius A. Okay. So if I apply the parallel axis theorem, so it's ICM times area is pi a squared times d squared, which is a squared. Okay. So this quantity is a quantity calculated when it's about the origin, and that's pi a to the power 4 over 2. And you get pi a to the power 4 here. So together you get 3 pi a to the power 4 over 2. Okay, so that's the same result as calculated using a double integral, okay, in the previous example. Okay. Yeah. All right. So another thing I also wanted to mention is that this application, and you have learned in your dynamics, okay, you can define, okay, an angular momentum as L equal to I times omega. Okay, so that's angular momentum. Okay. A linear momentum is mass times velocity, right? So this is the angular momentum, the moment inertia times omega. Okay. You also have this so-called conservation, right? Conservation of angular momentum, very much like conservation of linear momentum. Okay. So if there's no external force, you know, and there's no friction considered, then the angular momentum should be reserved, right? Same like linear momentum. Right? So this actually can explain many physical phenomena, right? Yeah. If angular momentum is maintained, for example, figure skating, right? You have watched figure skating. So often in time, as the performer goes, at the end of the perform, what they always do is they try to spin really fast, right? To impress the audience. So if you recall, how did they go when they spin really fast? They have to do what? They have to all the way shrink their arms to as close as to the center of the body. Okay, yeah. So that's exactly the reason you have if you have a conservation angular momentum, look at that. When you extend your arm, you have a bigger moment inertia. And when you take all your arm back to the center, you have a smaller moment inertia. So if the moment inertia is smaller and the L is the same, then the omega will be faster, right? And that's the point. Okay. If you go to Vancouver Science Center, they also have experiments, and there's a plate, okay, with some mass attached to it. So you can adjust the mass, the distance of the mass to the center. So if you let the plate go, right, you can observe which actually rotate fast all the way down to the bottom of the fastest. Okay, and that basically has something to do with the momentum. If all the mass is spread far away from the center, you have a higher moment and higher moment inertia. If it's all shrink to the center of the circle, the disk, then you have a smaller moment inertia, right? Yeah. Okay, so I think that's all I want to cover for applications of double integrals. Okay, so we'll revisit some of these applications, in particular moment inertia, and also this the concept of a center of mass when we learn triple integral and when we deal with 3D objects. Okay. So I only have a couple minutes left, so I think I can stop here. I don't want to rush up. So we'll start triple integral in the next lecture. Okay. Yeah. Any questions? Feel free to come over here.